Okay, we'll take a look at group problem solving one. So this problem, you're starting off with a brick. It's sliding down the slope of a house, and it has some uh, initial velocity associated with it. And it slides off the end and then lands on the ground a distance d from the house or from the building. Okay, so this is the work and energy problem as before. And what we actually need to solve is like this distance, right? How far away it is. So we have a work and energy problem here. And if you look at just from, um, sort of conceptually, we have some initial kinetic energy associated with this block. And also, we're at a distance, at a height off the ground. So we have some also potential energy associated with it. And the way we're going to handle this is we'll look at it from the perspective of, from work and energy. We have uh, some kinetic energy associated with it. And to go from point A to point B and then B to C, we're actually performing, gravitational work, okay, a work of the weight going down. So we can use work and energy to figure that out. We could actually come up with equations to represent, that you have some initial energy associated with initial kinetic energy, do some work, um, and then you have some, final energy. If you wanted to think about some work going from this point to this point, then we have some final kinetic energy associated with it. And our expectation, of course, is that going from here to here, the kinetic energy would increase. Now, the assumption we have to make here is, of course, that this is like a frictionless um, surface here, okay? Smooth surface. Uh, so we have an equation. We can come up. We have a working energy equation from here to here. We also have one from potentially from here to here, and we can have one from here to here also. Okay, and that will give us a relationship between working energy associated with, and we could actually determine like the velocities at these different points. Right? We could determine the x component of the velocity and potentially the y component of the velocity here too at each of these points. Okay. Now that helps us coming up with a velocity. And of course, if we're looking for its location, or if we're looking for position, you know, we would have to actually take a step back and look at one of our kinematic equations. So if we go back here and look at this, just pull this up. Here's some of the governing equations, right? We can use for this. We have our work and energy equation from going from A to B. Then we also have one we could go from B to C, or we could just directly go from A to C, right? We also have a work and energy equation associated with that, okay? Now, our end result here, of course, is we want to use this information, right, to give us our component here, like our velocity in the x direction. We want to use that velocity to determine our position, right, in the x direction. Now, if we look at it, we'd say, well, we have some initial position in the x direction. We have some velocity component in the x direction, which we could, use these equations to find that. And um, and then we have a time, right? So it's like, yeah, if you know the velocity in the x direction and you know its initial position, you know the velocity in the x direction, and you know the time that has transpired to get to that, or time that's transpired, you could actually figure out what the position is in the x direction. But right off the bat, you recognize, oh, okay, so yeah, we can use these equations to find the x component, but, and then of course we have an angle associated with it also. So we can find the x component, and the problem here, of course, is we don't know the time. All right. Well, we can also use these equations to find the y component, right? With the angle, we have the angle given here in this particular problem. Um, we could use a law of similar triangles here because we are given that. And from this equation, you could recognize that, well, yeah, the C, position C, is based on, whatever you were at B, which we know what that is. We were actually given that value. Its velocity in the y direction, and then the time. So to find the position in at C, which we know that it's going to be 0 right, from the horizontal, from the when it actually hits the ground, it's at 0 position. We'll use that as our reference point. And then when we find that and we get this equation, what we recognize is that, oh yes, this TBC is the only thing we don't know. So we could solve this equation for TBC, plug back into here, and then figure out what our position is in the x direction. So the first part of the equation, first part of the problem would be to use the work energy equations to find our velocities, use our vertical motion equation, come up with a time, and plug it back into here for our horizontal motion, and we can actually solve the problem. Okay? All right, so let's go through this kind of briefly. Okay. Okay. And this is really just the basic approach, right? So it's good to spend some time and really think about, your approach, how you would do that. Okay, so first part, apply principle in energy, come up with an equation that gives us our velocity at point B, okay? Now, B, this is our velocity off in this direction. So we could actually break this up into our x and y components because we have, it would just be, 4 over 5 times VB gives us our x, and the 3 over 5 gives us our y component, okay? So here's our unknown velocity. So solving this equation, you could, of course, solve for this and come up with 31.48 feet per second, okay? The second one is solving it for VC, right? Now we want to know what the velocity is at point VC, all right? So we can use that, and in fact, for this particular problem, this is like an intermediate result, which not necessarily you didn't necessarily need that for this part, but you could also do it directly from TA. And what you recognize here is that before we just used this 15 feet, right, to go from point A to point B, and now we're going to use 45 feet because we're going from point A all the way down to point C in the vertical direction. Okay, so here's our velocity at point C, right? Then now what we can do is, here's our x component of velocity. So here's our BC. Oh, yeah, right. So going from B to C, you could have also done it from, of course, from point A. Actually, you don't know what the distance is, so you couldn't do it. You could figure it out. But from point B, if we know the velocity at point B, of course, then it's easier. Then the only unknown is this distance going from D to C, right? Okay, so a little bit easier probably than doing it the other way where you go from A to B. You would have an intermediate distance that you really didn't need to solve this problem. So there was the point of finding the velocity at B. Okay, so this is the x component of the velocity, the 31.48 times 4 over 5, and that gives you some distance, which is some coefficient, times TBC. Now you can see in this equation, of course, we don't know what TBC is. Okay, so then you can apply the equation for vertical motion. And what you recognize here is the way the author did it, you have some choices. The author did it was saying that, oh, okay, we'll say YB is 0, and then YC is 30 feet down from that. So that gives you minus 30. Well, and then plugging in for the BY component, which is just this. And notice the direction of this. Of course, it's in the negative Y direction, so it's a negative value. And then the second part is gravity. Gravity being the component due to the gravitational. So this is my my acceleration, gravitational acceleration times 0.5 minus 0.5 because it's going down, and times the time. Okay. Now you could have said this was, of course, it could have been that YB was 30 and YC was 0. And what you would recognize, of course, the equation would be exactly the same for that. Okay. Now, just take a step back quickly here. Now going back to this, we can actually see if we go through and look at, just zoom in a little, drag it up. Okay. Okay. So going back and then coming up with the equation for that, you'll see you'll have your coefficients to use in the quadratic formula. You're going to have minus 16.1, minus 18.9, and 30. So that was just using the equation for vertical motion and coming up with those coefficients. Then you can use the quadratic formula, and from there, let me just go back. There, you can actually just find TBC, take this value, plug it back in, and then you can solve for D. Okay, and that's it. It was 22.6 feet. Okay, and that's